Greetings, I'm Neil. Welcome again. This chapter is all about, well, these guys, sort of. This chapter, it's all about the conservation of linear momentum and collisions, which is what's about to happen here with these wildebeest out here in Kenya on the Masai Mara. Now, much like we talked about on the chapter dealing with energy, the conservation of linear momentum, as far as we know, is a law that is not violated anywhere in the known universe, with the possible exception of when we get close to at the event horizon of black holes, where the laws of physics may very well break down. But with such an exception, this is a very powerful tool to have in your physics belt of tools in solving everyday problems. The conservation of linear momentum and the conservation of energy, both working in tandem with each other. Collisions, like what's happening here with the wildebeest migration, one of the largest, if not the largest, land migration on Earth. 3 million wildebeest migrate from the Masai Mara in Kenya over to neighboring Serengeti plains of Tanzania, looking for new grazing grounds. And of course, conflict is inevitable. So this chapter we're going to go through, if I were to pull up the chapter here, we'll talk about the definition of momentum, the product of mass times velocity. And a good segue here is to point out the fact that the definition of momentum might not be necessarily what the reader is used to hearing. For example, if you're looking at a sporting event and maybe one team is not doing so great, the other team is doing much better, they go into halftime, they've got a really good coach, great pep talk, and they come back out in the second half, and maybe the team that wasn't doing so well is doing much better. So the commentators may say, well, the momentum has certainly shifted in this game. Well, we know what they mean. The team that wasn't doing so great is doing much better. But that is really inappropriate use of the definition of momentum. Momentum really is the physical product of the mass of an object by its velocity. If the object is not moving, the velocity is zero, we've got nothing to talk about. The momentum is also zero. So in this chapter, we're going to talk about how we calculate the momentum of a single particle and how we can extrapolate that to the momenta of a multi-particle system. It's simply a matter of adding up the vectors of each individual momentum of each particle and summing those together. Because momentum is indeed a vector quantity because it's a function of velocity, and velocity is a vector quantity. So we talk about determining the center of mass momentum in this chapter. And once we've gotten the derivation of how to calculate the center of mass momentum, we can apply this to the conservation then of linear momentum. Now, the conservation of linear momentum, much like the conservation of energy, says that for a closed or an isolated system that is not interacting with the outside world, the total momenta is always a constant quantity. Now, the individual momentum from one particle to another may shift based on collisions, etc., but the total momentum of the entire system, if it's isolated, will always remain constant for the end of time. And this is essentially what the conservation law says. Now we can talk about collisions, what happens when things collide. Collisions are inevitable in life. Some collisions are necessary, others not so fortunate. In general, when two objects collide and they bounce apart, we call this an elastic collision. If the objects collide and they stick together, we call this an inelastic collision. So different energy rules apply, as the reader will find out as we go through this chapter in some detail. So the center of mass, as we've just mentioned, is important in talking about the entire system as it moves as a whole. How do you calculate the center of mass? Well, that also is dealt with in this chapter. For a three-dimensional object that has volume, we can easily calculate the center of mass, and the chapter shows the intrinsic details of how to go about this. Now, one of the examples that we've used here is this is taken on the island of Gotland in Sweden. It's in the Baltic Sea, really the middle of nowhere. It requires a 5-hour ferry ride from Stockholm, Sweden, to get to this island. It was Viking Central about 1,000 years ago, and we can see the shape of these rocks they make here a ship. Vikings are known as avid ship builders, and among other things, which they don't necessarily get credit for very often. It's not just the pilfering and plundering that we're used to hearing about Vikings. They were actually merchants and builders, etc. So this here is a Viking graveyard. They were buried in places like these. So I discovered this one. I hope I'm not desecrating the grave by standing on this rock. I wasn't aware that I am, or was. I hope I wasn't. In any event, this is a segue. This Viking burial ground on the island of Gotland, which was no easy task to get to. Well, we've generated an example for the collisions of two ships, maybe a Viking ship and one of the ships that they were about to pilfer and plunder, maybe a merchant ship. So we look at this collision, and as they collide, this is an elastic collision where they go off in different directions. So it's a good example for the application of vectors, where we've got different directions to consider both before and after the collision. So we go through the calculation using the conservation of momentum in each direction, both the x and the y independently, and then we can use the Pythagorean theorem to solve for the overall velocities, as we've done. In many situations, the mass is not conserved. The mass it changes over time. So how then does this affect the momentum of the system? Well, rocket motion is a prime example of this. Unlike cars, which the tires, they use friction to push against the roadway to get linear motion, or airplanes, the engines, they take in air and they squeeze it, they compress it, and they push the air out the back, so they create a forward thrust, and then the shape of the wings do the rest to create lift. No such luck if you're a rocket and you hope to leave the confines of our atmosphere around the planet. There is nothing to bite into or push against to create motion. So rockets, they carry tremendous amounts of fuel, so they burn the fuel at a rapid rate to produce an exhaust. And in turn, the expulsion of the exhaust out the back of the rocket creates a forward thrust, so the rocket can accelerate. So this is, in effect, rocket motion. It's all about the conservation of momentum if we consider the entire system of the rocket plus the exhaust that it kicks out the back. And that defines our system. So the conservation of both of these together will help us determine the conservation of linear momentum, as you can see here as an example of a 747 aircraft as it pushes against the air to create lift. It's got even something as very heavy and massive as a 747 aircraft can use something as simple as the atmosphere to push against at the right speed, of course. Again, no such luck if you're a rocket. You need to generate your very own atmosphere. So we have derived the equations governing the motions of rockets as they expel mass. That is, we've done some rocket motion in this chapter, so the reader might be quite interested in learning how this happens. To some small extent, the reader can claim that they know a bit of rocket science once they get done with this chapter, as we derive the equations of rocket motion using the conservation of momentum and collisions involved. Here's an example from the Kennedy Space Center of the Atlantis space shuttle, which does just that. It expels a lot of fuel on takeoff, typically the rate of about 100,000 pounds of rocket fuel, which is a mixture of liquid oxygen and liquid hydrogen and kerosene mixed together, gives you rocket fuel, and it goes through a lot of that to create what's called the escape velocity to leave the confines of our planet's atmosphere and overcome the Earth's gravitational pull, so the shuttle doesn't go up and come back down. It needs to create what's called an escape velocity. It's different for each planet. For the Earth, it's about 11 kilometers per second, or 7 miles per second. So that's, the rocket, the space shuttle needs to generate that much of an escape velocity if it hopes to keep going and not come back down like that. So we derive all of these things. It's quite interesting. You can see the main fuel tanks. I've shown some pictures here of one of my trips to the Space Center. And really fantastic pictures showing you how much fuel is actually carried to generate the escape velocity needed by rockets. Now, as we apply the conservation laws to get to where we need to go, which is in space. So, and we've got several examples of rockets in motion and how much fuel, the rate at which the fuel needs to be burned to generate the thrust that's necessary to get to a velocity that we need to. So these are quite useful equations. So you can see the back of the Saturn V rocket, the most powerful rocket ever built by the hand of man. It's on display at the Kennedy Space Center in Florida. And so it really shows the reader, if you were to go see this with your own eyes, how massive these thrusters are in the back. It's testament to how much fuel is burned and at what rate they're burned to create such tremendous amounts of force to lift the rocket, plus its fuel, plus its payload, off of the launch pad. In excess of 7 million pounds of thrust is generated by these rockets. So it's really no joke how much fuel needs to be carried. So we derive some equations for the rocket motion, and the reader gets a great sense of this. And there are several additional problems. This is one taken, this is a picture I took of seals on an ice floe, an iceberg in Antarctica. Not a safe place to be, because there are also killer orca whales that they hunt seals on the ice like that, which I also captured on some video. And we made an example of this in calculating the center of mass of this three seal system. And so it's a quite interesting example of how we can use just something as mundane as seals laying around, although there's nothing mundane about being in Antarctica. And just more examples of the Saturn V rocket on liftoff and some calculations to determine escape velocity, etc. And we finish off with another problem on elastic collisions. And this particular problem was a very in-depth problem and a lengthy solution, which again is these are the best types of problems, because this problem takes into consideration Newton's laws, the conservation of momentum, and energy conservation all wrapped into one, being used in the solution of one problem. So these are the best types of problems to learn from, because it takes into account many things that the reader will need to get practice in order to be proficient in problem solving for exams, etc. So I hope this chapter is very helpful to you. Thanks again.